know. And the equation is called the ideal gas law. The ideal gas law is PV equals nRT. Okay. So, good equation. I'll give you this on the exam, but obviously some of you want to go to medical school or are taking MCAT or whatever big exam that you guys are going to be taking. You may want to memorize this equation. P is pressure. So the units of pressure is many units. One of the units is atmospheres. This is the one we're going to use a lot. Okay, ATM stands for atmospheres. Okay, you may see millimeters of mercury. That's a unit of pressure. Pascals is a unit of pressure. So, yeah. Okay, but this is the one we'll probably use in our homework problems and our test problems, test questions. Okay, pressure is force per unit area. So not going to test you on definitions of pressure, but it's a force. When you have more collisions, you have more force. Okay, so pressure is force per unit area. So this is our definition of pressure. Okay, so more collisions, more pressure. Less collisions, less pressure amongst the gases. We're talking about gas molecules now, okay? So, if you breathe in, breathing in oxygen, breathe out, you're breathing out carbon dioxide. Those are gases, right? So that carbon dioxide, the oxygen, they're all hitting and colliding with each other. Okay, so more collisions, more pressure. Right, so this is the pressure. So gases will exert a pressure. Okay. All right, this V here is volume. So gases, like a liquid, like my water bottle here, will occupy a volume. Okay, units here, probably you'll see it as liters, maybe. Okay. For this equation. So gases occupy, just like a liquid, you know this, okay? They'll take up the volume of the container. So gases occupy a volume, just like this liquid is occupying 700 milliliters according to the bottle. N is the number of moles. Okay, so gases occupy a number of moles. Okay, so, you have this many moles of a gas. Gases, I should say, gases occupy a volume. They have a number of moles. Okay, and this T is temperature. Okay, by the moles. Okay, the units here are MOL, moles. And then finally we have T, which is temperature. Okay, temperature T. And the fourth thing is that gas is very much responsive to temperature. Gases react to temperature. You've raised the temperature. What do you think will happen? More collisions. Gases will get more kinetic energy. Okay, so gases really respond to temperature. Okay. All right, so I want everyone to please, understand this. Temperature must be in Kelvin. Okay, Kelvin. This is an easy thing to get points off. Kelvin. Okay. You have to convert your temperature to Kelvin anytime you're dealing with the gas law. So, I've been in this school for 8-9 years, and every time, in this equation, they put it in degrees C. And that's not correct. Okay. Ever wondering, not that it's important, why can you not put degrees C here? Let's say the temperature is really cold outside and it's negative 20 degrees C. Okay, if you put negative 20 degrees C, what happens? That negative becomes negative N. You cannot have negative number of moles. You cannot have negative pressure. You cannot have negative volume. There's no such thing. Okay, so that's why we always convert to Kelvin, because Kelvin has no negative numbers. Okay. So what is the formula to get to Kelvin? Okay. 273. Okay, so you must add 273 here. Right, so this is the formula, PV equals nRT. This is the ideal gas law. Pressure, volume, NT, all of this comes together with R, so I'll give you R on the test. Okay, you don't have to worry about it. Okay, R is 0.0821 liters times atmosphere divided by mole Kelvin. Okay, I give you that, okay? I'll give you that. You don't have to memorize it. All right. So I'm going over some units here. Pressure is going to be in atmospheres. If you see millimeters of mercury, this is the conversion, but I will give you that. Okay, I'll give you the conversions. You do not memorize it. You do not memorize R. Okay, don't. Okay. Most important thing, what will you do to your temperature? Convert it to Kelvin. Take degrees C and add 273 to it. Okay. All right, here's another conversion to Pascal. The PA is Pascal. This is a unit of pressure. Again, I will give you that. You do not memorize it. Okay, PA is Pascal, another unit of pressure. All right, some properties of gases. I'll explain this to you, so just read along with me. Gases assume the shape and volume of the container, just like a volume. Okay, so this room may have 100 gases. It could have 1,000 gases. They all fit into this room. Gases are the most compressible state of matter. Okay, have you heard of a piston? No, a piston? No? Yes. Pistons that run your car. Okay, so you can compress a gas, and it's very compressible. Okay. Oh, I know a good example of property number 2, hairspray. Okay, that is really compressed, or a Coke can, soda can, right? What happens if you open that soda can? Psst. Okay, this is the escape of gas. Okay, what happens when it hairspray? Okay, it's very compressed gas inside. Okay, why do they tell you, just talking off the cuff here, why do they tell you don't put hairspray near heat, or don't throw it in a fire?
Because the can will explode.
It'll blow up. Okay, why will it blow up?
Because of the pressure.
Right. Okay. The high temperature make the gases just go around like crazy, the kinetic energy, and then it just breaks the container. Yeah, it blows up. So, Coke cans, hairspray, this is gases that are very, very compressed. Gases will mix evenly and completely in the same container. So this idea is that gases do not separate. Okay, it's not like oil and water. Okay, if you breathe in, see it, breathe out, it mixes in. It's not like all the gas goes here and all the oxygen goes there and all the helium gas goes there. Okay, this is not like liquid and water, oil and water. This is not like oil and water. Okay, so this term that we use is called miscible. If you take Chem 2, they talk a lot about miscible and not miscible. Miscible means they mix. Okay, so everybody breathe out, everybody exhale. As they exhale, all the gases that we've exhaled out have mixed. Okay, it's not like, it's not like oil and water. Okay, so whether you have 100 gases or 50 gases, or even 2 gases, they'll mix evenly and they'll diffuse, okay, evenly. So this is not like oil and water. Okay. Property number 4 of gases, they have lower density than liquids and solids. Heavier gases often rise to the atmosphere. Okay. Property 5 of gases, property 5 of gases is that gases diffuse and spread out. Okay. So gases diffuse. Okay. So the motion is kind of like a zigzag. Okay, kind of like a zombie walk. That's the motion of a gas. Okay, they diffuse. Okay. It's never a straight path. And what do you think influences diffusion rate? Okay, what influences diffusion rate is diffusion rate. What influences the diffusion rate is the molecular weight. Let me clear my throat. What influences the rate of diffusion is how big the molecule is. That's the molecular weight. Okay. The higher the molecular weight, the bigger the mass of the gas, the speed of the gas goes down. Okay. Heavy gases diffuse slowly. Okay. If you're a big bulky gas, you're not going to move as fast. Okay? Just like our track team, they are really, really lightweight, so they are super fast. A gas which has a large molecular weight will not diffuse as fast. Its rate of diffusion will not be as fast. Okay. Conversely, if you have a very low molecular weight gas. Okay, probably the lowest molecular weight gas there is hydrogen gas. Okay, maybe helium gas if you look at the weight in the periodic table. So low molecular weight, these will diffuse faster. They will have a greater speed. Okay. So I'm just talking to you guys about what influences diffusion. Temperature. Okay, if you increase the temperature, think of your hairspray. Okay, what's going to happen to the diffusion? Up or down? The speed? Up. Okay, up. Okay, that's why the hairspray doesn't go in the fire. Okay, it's combustible or flammable. If you lower the temperature, the gases move slower. Their kinetic energy is lower. So what two factors influence how fast a gas moves? We call that diffusion. It's the molecular weight and the temperature. Okay? There's an equation that we'll get to at the end of the class that talks about this. So these are the two things. All right, and final property number 6 of a gas, the higher the pressure of a gas, the more collision between the gas molecules happens or occurs. Okay, so that's good. So just some basic properties of gases there. Here is our equation, PV equals nRT. We'll do some problems related to that. Okay, the next thing I want to talk to you guys about is something called STP. Okay, this is another thing that kind of gets students a little bit confused. Okay. On page 4 of our notes, there's something that is talked about called STP. Okay, STP stands for this: standard temperature and pressure. So here's what I want you guys to know about STP in terms of like a multiple choice or short answer on any exam. The standard temperature in STP is going to be 0 degrees C. Everything is in Kelvin, so really it's 273 Kelvin. Okay, that's the standard temperature. Okay, the standard pressure in STP is 1 atm. Knock, knock. So these are the two things with regards to STP. That's all, that's it. Okay? So STP is 273 Kelvin, 1 atmosphere pressure. Okay, that's all you need to know. Okay, now, I'm going to give you a situation here. Okay? Now, I want you to imagine you have 1 mole of an ideal gas. Imagine you have 1 mole of an ideal gas. Okay, how much volume at 1 mole of an ideal gas at STP? Okay, let's calculate the volume. Okay, let's calculate the volume V. Okay, so PV equals nRT. Okay, we're doing this at STP now. V equals nRT over P. All right, like I mentioned before, we have 1 mole of the ideal gas. Imagine we just have 1 mole. Okay, any gas, okay? Okay, R is, I'll give you it, 0.0821 liters times atmosphere divided by mole Kelvin. Okay, that's R. Okay, so that's a constant. 1 mole is, imagine you have 1 mole. What is T here at STP? Something you guys should know. It'll be 273 Kelvin. And what is P pressure at STP? 1. Okay. So if they say STP, you have to know 273 Kelvin and you have to know 1 ATM. If they say STP, it's 273 Kelvin, 1 ATM. STP. Okay, 273 Kelvin, 1 ATM. That's all, that's it. But let's just say I give you 1 mole, or we have 1 mole of a gas. Okay, we solve for this. Let's solve for that. Okay, by the way, moles cancel. Kelvin cancels. ATM cancels. Okay, we're left with liters. So 0.0821 times 273. 0.0821 times 273, okay, divided by 1. Okay, 22.4, and my units left over are liters. Okay, so this is the volume of 1 mole of an ideal gas at STP. Okay. Volume of 1 mole of an ideal gas at STP. Okay. So what does this mean? Okay, this is a really weird thing in nature, Mother Nature. It's really quirky. Let me tell you why. So let's say we have oxygen gas, okay, and you're at STP and 1 mole of oxygen gas. How much volume do you have of the oxygen gas? 22.4. Let's say you're helium. How much volume at STP for 1 mole? Okay, let's say you're carbon monoxide, which is the poisonous gas. How much volume if you're at STP and 1 mole? Okay, what about carbon dioxide? Okay, one of these is poisonous, one of these is essential for life, one of these is used to fill up balloons, one of these is found in your lungs a lot, CO2. What is the volume of 1 mole of CO2 at STP? Okay, so I mean, no matter how big, no matter how small, no matter how toxic, no matter how nitrogen gas, 22.4. Okay, there's a gas called UO2, uranium dioxide. Okay, some weird, crazy gas. If you have 1 mole of it at STP, the volume is 22.4 liters. So how big, how small, how anything, regardless of its properties, it will always have 22.4 at STP if you are talking about how much? 1 mole. Okay, the key here is 1 mole. Now, the question here on an exam or short answer to throw you off, is 1 mole a part of STP? Yes or no? No. No. Is 22.4 liters a part of STP? No. No. So on an exam, 22.4 liter, STP means 22.4 liters of gas. No. That's not STP. What is STP only? 273 Kelvin and 1 atmosphere. Okay? Right? Can we not get confused? Okay, what is STP? This inside the pink circle is only STP. What happens if you have 1 mole of a gas, 1 mole of an ideal gas at STP? Now you can say it has a volume of 22.4 liters. Okay? So don't get confused. Okay? Don't get confused. Okay? So very important key here in the sense that many students in previous semesters will say this is STP, it's not. Many students previous semesters will say 1 mole is part of STP, it is not. Okay, STP is this and this only. Okay, that's all. All right, let's go over some of these laws here. Okay. I'm going to go to page 5 here. Okay, these are derived from the ideal gas law, PV equals nRT. If you make N constant, R will always be a constant if you keep the temperature the same. Okay, if I have a pressure P1 at some volume V1, I change the volume. I change the volume to V2, I'll get a new pressure P2. Okay, this is called Boyle's law. Okay, this is constant N, R, and T. This is the only law, individual gas law, that is inversely proportional. As one goes up, the other goes down. Yeah. Which means as your pressure goes up, your volume will go down. Okay? That makes sense. Okay, imagine if I have class and say, okay, class, we're not going to meet here, we're going to meet in that broom closet. Okay, our volume has gone significantly down and our pressure has gone way up. We'll be shoulder to shoulder. We'll be uncomfortable. Okay, that's a lot of collisions, human collisions. Okay, so this is called Boyle's law. Boyle's law. The other laws, the other individual laws, are going to be direct. Okay. Okay, one of them is called Charles' law. Okay, Charles' law. I have a volume V1 at some temperature T1. Okay, I'm going to change the temperature. I'm going to change the temperature to T2, and the new volume will be V2. This is like, a piston compressing or depressing a piston. Okay, this is why your hairspray explodes, because you raise the temperature so high, it's going to bust through the container because the volume is expanding so much. Okay, so this is called Charles' law. And what do we have that's constant here? If I keep the pressure constant, R is always constant, and N is constant, number of moles. Constant N, R, and pressure P. Now, as far as this Charles' law is concerned, this is a direct relationship. This is directly related, direct proportion. Okay, which means that as you increase the temperature V1, or if you increase the temperature T1, the volume V1 will increase. Okay, if you decrease the temperature, your volume will decrease. Okay, as one goes down, the other goes down. Okay. So as T goes up, the volume goes up. Okay, This is why you cannot put hairspray near high heat, okay? Because the volume will expand so much. This is called Charles' law. Right, the next individual law that I'd like to tell you guys is called Avogadro's law. Okay. Avogadro's law. So Avogadro's law, we have some volume V1, and there's a number of moles inside that volume. Okay, we'll add or decrease the number of moles. Okay, we'll increase the number of moles to N2. Okay, maybe we'll decrease the number of moles to N2, number of moles 2. As a result, we'll get a new volume V2. So here the constant is going to be pressure. R is always a constant at 0.0821, and this is at a constant temperature. This is directly related. Okay, this is a direct relationship. As one goes up, the other goes up. Okay, as you increase the number of moles, the volume will go up. If you decrease the number of moles, the volume will go down. Okay, what is an example of Avogadro's law? Inflating a balloon, okay, or pumping a bike tire, or inflating a basketball. All of these are examples of Avogadro's law. Inflating a basketball. Or, I don't know, pumping a bike tire or inflating a balloon. So these are all examples of Avogadro's law. Inflate or deflate. Okay, there's one more law that's not in here. I think this is called Guy Antione's law. I do not know the name, okay? But it's this one here, okay? I am so sorry, the name escapes me, but pressure P1 at some temperature T1. Okay, we will increase or decrease the temperature to T2, and we'll get a new pressure that is called P2. Okay, here what is constant is the volume is constant, so we have to try to keep the volume constant. And then constant N, and then R is always a constant. It's the gas constant. And this is directly related as well. Okay, so as you increase the temperature, the pressure will go up. Okay. If you decrease the temperature, less kinetic energy, less collisions, the pressure goes down. So, I do not know the name of this, but this is the relationship that you should know. So what should the temperature be if we're going to use this equation? What units? Kelvin. What should the temperature be if you're going to use Charles' law, this equation? Kelvin. And then finally we have some combined gas laws. We will combine Boyle's law, Charles' law, Avogadro's law, this law. We can combine all the different laws. So let me give you those. We have P1 V1 over T1 is equal to P2 V2 over T2. Okay, this is a constant number of moles. and R is always constant at 0.0821. Excuse me. We have a Boyle's law here and a Charles law there. Okay, you see how they're combined together. Okay, the Boyle's law and the Charles law. And then we can combine the Boyle's law. Here's one more. P1 V1 over N1 equals P2 V2 over N2. Okay, this is combining the Boyle's law P1 V1 over the Avogadro's law V1 over N1. Okay, combining them. Okay, this is a constant temperature. R is always constant. It is the universal gas constant. So we can combine these gas laws as well. So this is the basis for some of the homework problems and some of the problems that we will do together in class. Right, you see this little thing, PTV. Okay, so here's something that you may find interesting. You hold one of these constant. The P stands for pressure, the T stands for temperature, the V stands for volume. You hold one of these constant by putting your finger over it. Okay, if I raise the pressure, what happens to the volume? Goes down, okay? Right? If I lower the pressure, what happens? Volume goes up, okay? If I keep the pressure constant and I raise the temperature, what happens to the volume? Goes up. And if I lower the temperature, what happens to the volume? It's going to go down, okay? If I keep the volume constant, okay, don't change the volume. If I increase the temperature, what happens to the, if I increase the temperature, what happens to the pressure? Goes up. If I decrease the temperature, what happens to the pressure? Goes down. Okay, so just keep one of the three constant. Okay. All right, let's do some practice problems here. So calculate the volume in liters occupied by 2.12 moles of nitric oxide at 6.54 atmospheres and 76 degrees C. So now we'll do some problems together. So calculate the volume V. Okay, what is this 2.12 moles of nitric oxide? We'll call that N. What is 6.54 atm? Pressure P, and what is temperature? T, but what should we put it at? Kelvin. Okay, so I'm going to quickly add 273 here and get it to 349 Kelvin. And what do we want to find? Okay, we want to find the volume in liters. Alright, so we'll do PV equals nRT, and we'll solve for V here. Equals nRT over P. Okay, so this is straightforward plug and play. Plug it in and get the answer out. N is 2.12 moles. Okay, the gas here is nitric oxide. R is, I'll give you R, it's 0.0821 liters times atmosphere over mole Kelvin. T is temperature, but always put it in Kelvin. So for that, we will add 273. And then pressure P is 6.54 atmospheres. So this is just plug and play. Okay, the moles cancel, the Kelvin cancels, the ATM cancels. Okay. So we have 2.12 times 0.0821 times 349 divided by 6.54. What did you guys get? 9.29 liters? Okay, something like that. 9.29 liters. Okay, this is our answer. All right, how about this problem here? What is the volume in liters of 49.8 grams of hydrochloric acid gas at STP? Okay, gas. This is all gas laws, so these are all. What is the volume in liters of 49.8 grams of HCl at STP? All right, so what is STP? There's two things that only make up STP. That's all. What are they? (273 Kelvin and 1 atmosphere pressure). Okay, and it's asking for the volume. And we got our STP. Let's go ahead and convert this to moles, the HCl. So 49.8 grams of HCl times 1 mole of HCl contains how many grams? Hydrogen is about 1.01 at the periodic table. Chlorine is 35.45. It's about 36.46 grams. The grams of HCl cancel. So 49.8 divided by 36.46, about 1.37 moles. Okay, are you guys getting that? 1.37 moles of HCl. All right, so volume is what we're going to solve for here. PV equals nRT. V is equal to nRT over P. Okay, N here is 1.37 moles. R is 0.0821 liters times atmosphere divided by mole Kelvin. Temperature T, what is our temperature T at STP? I think you guys mentioned it. It's 273. And then what is pressure P at STP? 1 atmosphere. Okay, the ATMs cancels. The moles cancel. The Kelvin cancels. And so notice the answer is not 22.4 liters. Okay, that's not the answer. We have 1.37 moles, not 1 mole. So 1.37 times 0.0821 times 273, getting about 30.6 liters. Okay, 30.6 liters. As the answer. All right, let's do this problem here. A sample of gas initially at 0.97 atm, pressure 1, is cooled from 21 degrees C T1 to minus 68 degrees C T2 at constant volume. What is the final pressure? This should say pressure, sorry about that. Okay, what is the final pressure in atmospheres? ATM is a pressure, not volume. All right, so what equation will we use here? Okay, we have P1, we have T1, and we changed the temperature to T2, and this will give us a new P2, which is what we're trying to find. Okay, so that's the relationship. Okay, P1 over T1 equals P2 over T2. All right, so we have P1 here at 0.97 atmospheres. T1, 21 degrees. Let's convert that to Kelvin. 21 plus 273 is 294 Kelvin. P2 is what we're trying to solve for. And then T2 is a minus 68 degrees. Let's convert that to Kelvin. We'll take minus 68 and add 273 to it, 205 Kelvin. All right, to solve for P2, we will cross multiply. So let's cross multiply. P2 is equal to 0.97 atm times 205 Kelvin divided by 294 Kelvin. And Kelvin cancels. 0.97 times 205 divided by 294. 0.68 atm. Okay, so this is using one of those gas laws. All right, let's do a couple more problems, practice problems before we close shop for today. There's one more problem in the back of the, yeah, go over here. Can you guys read this here? Okay. All right, a gas initially at 4 liters, 1.2 atmospheres, and 66 degrees C undergoes a change so that the final volume, okay, so we have a volume V1, pressure P1, and temperature T1 undergoes a change so that the final volume, I'll call it V2, and temperature T2 are 1.7 liters and 42 degrees C, V2 and T2. What is the final pressure, P2, of the gas? Assume the number of moles of gas remains unchanged. Okay, so this is going to be a individual gas law, but it's actually combined. Okay, so what's the relationship between P and V? Okay, it's P1 V1 equals P2 V2. And what's the relationship between P and T? Or what's the relationship between V and T? Okay, it's the same. Okay, V1 over T1, or P1 over T1. V2 over T2, or you can say P2 over T2. So this is a combined gas law. Thanks. So this is the equation we need to know. This is initially, we change certain things, and then this is the result of changing those things. Here we changed the temperature and volume. All right, shall we go ahead and do this now? Okay, P1. What's P1 here? P1 is 1.2 atmospheres. Okay, V1 is 4 liters. Divided by T1. What's T1? We must convert to Kelvin. 339 Kelvin. Okay, P2. What we're trying to find, correct? What's V2? 1.7 liters, and then what's T2? What's 42 plus 273? 315 Kelvin. All right. Let's cross multiply this to solve for P2. So I'm going to cross multiply. So 1.2 atmospheres, 4 liters, 315 Kelvin, okay, divided by 339 Kelvin times 1.7 liters. Okay, this is going to equal to P2. Okay, the Kelvin cancels, the liters cancel. So it's going to be 1.2 times 4 times 315 divided by parentheses 339 times 1.7. Close those parentheses. 2.6 atmospheres. 2.6 atmospheres. Okay. Okay, so this is our answer. This is the combined gas law. All right, so here's an equation that I'll give you on the exam. You can actually find the molecular weight of the gas if you know the density. Okay? If you know the density, what is density? It's mass over volume. Remember this? Okay, so if you know the density of the gas, you can get its molecular weight. Okay, likewise, if you know the molecular weight of a gas, if you know the density of the gas, you can get its molecular weight. If you know the molecular weight of the gas, you can get its density. Okay, so some equations that are derived from the gas laws. Units of molecular weight are going to be grams over moles. Okay. Grams per mole. All right, let's see if we can finish up page 9 and then see how we feel from there. Okay, you still got a good 15 minutes or so of class. All right, so we've discussed some gas law problems, Boyle's law, Charles' law, so on and so forth, Avogadro's law. We did some practice problems, so this and a couple of more items, and we will be good to go for chapter 5, and that will end the material for our test. All right. So another problem. A 2.14 liter sample of hydrogen chloride gas at 2.61 atmospheres and 28 degrees C is completely dissolved in 668 milliliters of water to form HCl aqueous. Calculate the molarity of the acid solution, assuming the volume stays the same. So on our exam, we should know that molarity is moles over liter. Okay, more specifically, it's moles of solute over liters of solution. So our solute here is going to be hydrogen chloride. Okay, our solvent is going to be water. Okay, why is our solvent water? Because of the aqueous. Okay. All right, so let's use PV equals nRT to get the moles of the gas. Okay, PV equals nRT. Okay, and then the moles of HCl is going to be PV over RT. Okay, PV over RT, yeah. Okay, this is the number of moles of HCl. All right, our pressure here is 2.61 atmospheres. Okay, our volume here is 2.14 liters. Okay, R is something I'll give you. It's 0.0821 liters times atmospheres divided by mole Kelvin. And temperature T, don't forget to convert it to Kelvin. 273 plus 28, what is that? 301?
Yeah.
This is our moles of HCl. Okay? It's 2.14 liters of the gas. Right, ATM cancels, liters cancels, Kelvin cancels. The moles in the denominator of a denominator move up to the numerator. Okay, so our answer will be in moles of HCl. So 2.61 times 2.14. Okay, divided by parentheses, 0.0821 times 301. We get about 0.226 moles. So 0.226 moles of HCl. This is our moles of solute. Molarity is moles of solute. Well, we got that here. Over liters of solution. So what is our liters of solution going to equal to? It's going to equal to our 2.14 liters of solute HCl with our 668 milliliters of solvent water. And let's convert that to liters. How will we convert this to liters? 3 to the left plus 0.668 liters. Okay, doing that really quickly, the liters of our solute plus solvent, 2.808 liters of solution. Okay, so molarity, big M, is going to be of this HCl. This is the concentration of HCl in the solution, is going to be 0.226 moles of HCl. Okay, divided by 2.808 liters of HCl. And what do we do when we get that on our calculator? .080 or something, big M. that's the calculations you'll go through to get the molarity, okay, the concentration of that solution. Right, so we do one more, or do you want to call it a day? 10:35. So Thursday we'll finish up this chapter, and then we'll start our review, and then Thursday we'll also, do a little review as well. Okay, and then I think after that is your fall break, right?
Yeah.
Fall break, which is Monday and Tuesday. So you come back from fall break, taking your exam. Okay, so we'll finish this up on Tuesday and do a little review as well.